So we're all familiar with the optical fibre network, and when we think about fibres, we tend to think of the long, thin strands of silica glass that are used in these networks. So obviously these silica cables enable us to transmit data over thousands of kilometres at the speed of light, and this is obviously really important because this ability to transmit data in real time has huge economic costs and also huge societal benefits. So the fact that these fibres can transmit the data is enabled by a couple of key properties. Obviously, it's very low loss, but more importantly, it's passive. So the data is transmitted without undergoing any distortions. But if we want to build an information network, then we need to be able to do a few more things. I mean, first of all, we obviously need to generate our signals. We then need to be able to modulate them, switch them, route them around our systems, and eventually we need to be able to amplify and detect them. So there are some things that we can do with our silica glass fibres to perform some of these functions. In particular, a key example is the optical fibre amplifier, which can also be used as a light source. And importantly, these amplifiers can be spliced into our optical networks so they do not disrupt the transmission of data. However, for pretty much everything else that we want to do, we rely on the electronics. And as we learned yesterday, if we're thinking about the electronic domain, then this is the home of semiconductors and metals. In particular, the most famous semiconductor is obviously silicon. So at some point we need to interface these two technologies, our fibre platforms and our semiconductor platforms. And when we, typical example of where we may want to do this is something like a data centre. So into this data centre comes our long haul cables. You can also see a couple of other cables that do short reach as well. But every time we convert between this electronic domain and the optical domain, this not only costs us in terms of speed, but it also costs us in terms of energy. And this energy cost is huge. As we learned yesterday, it can be up to 10% of the global energy consumption. It also generates a lot of heat. So every time we have these big electronic servers, then we need to have huge cooling fans. So there's another vision for this, and that is what happens if we move some of this electronic processing into the optical domain. And perhaps the most popular choice for doing this is silicon photonics. And the main reason for wanting to do silicon photonics is because all of our electronics is done in silicon as well, and therefore you can have your silicon optical platform directly linked to your electronic platform. However, there is a problem with this, and that silicon photonics, the size of this is very small. So when we try to interface this silicon photonic platform with the outside world, we have another challenge, and we're going to throw away a lot of energy. Now, this is not really to scale, but it's just to give you an idea of what the problems we're facing. So the solution that we're looking at in my group is what happens if we can introduce those semiconductor materials directly into the fibres themselves, and therefore we can bypass this connection problem. So now we have a fibre that can transmit your data, can potentially process your data, and even potentially read it out, as I'm showing here. So you may think, how could we make one of these fibres? Well, we start with a standard fibre fabrication technique, and first of all, we need to make a preform. So this is essentially a macroscopic scaled-up version of our optical fibre. So we can sleeve the different materials inside this glass preform, and then we take this macroscopic preform and we feed it into a fibre drawing tower, and hopefully when the next slide comes up, you'll see that we have the fibre drawing tower, we have a heating element, and then we draw our macroscopic preform down into some sort of microscopic scale. Now, in order for this to work, we need to make some careful choices about our materials and also about the draw speed and the temperature we're using. But by using this technique and a sort of a variety of variants of this, we've made a range of different semiconductor fibres, and I should say not all of these have come from the groups that I've worked with. But as you can see, they've got a variety of semiconductor fibres, we've got two-dimensional fibres, we've got fibres with heterojunctions, and we've also got fibres with metal probes in them now. So my group's largely been working with the silicon microwires because this is analogous to your microwires on chip. And using these silicon microwires, we've done a number of demonstrations. These are cartoons, but I can assure you the experiments are real. So the first thing we've done is obviously we've modulated the data. So this is using a high-powered data stream to modulate a CW signal. We've then done a similar experiment where now what we're doing is switching data from one wavelength to another. So you could potentially use this to route around your systems. And then the final experiment I'm going to show you is where we take our silicon microwire and we embed a metal inside the center, and now we can use this for optical detection. So essentially in this fiber, what happens is your light comes in, you convert your photons to an electronic signal, and you read it out. So all of these demonstrations are done on sort of picosecond to femtosecond timescales, so this is very fast and it's comparable with your electronics. So you might ask, why aren't we using these fibers in real-world systems? Well, obviously there's a couple of other metrics we have to worry about. So although the speed is good, the energy is too high. Also, we have some other challenges in terms of cost, scalability, and reliability. So once we can solve these problems, then there's a whole host of things that we can do with these fibers, and obviously data processing is a key one. And what's really significant about the fibers that we work with is we can actually post-process them, so we can actually have different elements of our fiber that perform different functions. So we now have fibers that can transmit, modulate, switch, and potentially detect at the end. So we can then think about weaving these fibers into smart textiles. So this is just a pretty image, but you could imagine if this was an optoelectronic fiber, you could then use this for a sensor, you could use this for health monitoring, or you could even use it to connect to something like the Internet of Things. But just finally, I wanted to conclude on a positive note, so I thought I'd show you an application where these fibers are in use, and this is for medical probes. So these fibers have metal wires down the side, and these metal wires detect changes in transmission, and this tells you whether you've hit a defect. So hopefully this shows you some of the commercial value of these fibers, and hopefully if we can improve some of those other properties, then we can see a lot more opportunities for them. So thank you.
That was really, really interesting talk, and I think the only thing I wanted to pick up on is obviously you use silicon because you were talking about integration with what we already have, but silicon's not a particularly great photonic material. No. Semiconductor. Have you done any work on different semiconducting materials? Yeah,
so we've worked with a range of different semiconductors, none of which you probably would identify as being good photonic materials. We've worked with silicon, we've worked with germanium, we've worked with zinc selenide. We're working with silicon because this is where the interest is. But as you've identified, at some point people are going to realize that maybe silicon isn't the best option, so we have to look elsewhere. It depends on what sort of process you're using to fabricate these fibers to how broad we can sort of make the library of materials that we can work with. So as I said, you have to choose these materials right to embed them in the fibers. But I think there's a lot of other materials that we could use that probably would be better than silicon. So if the community moves away from silicon, that would be great.
So actually, normally a regular optical fiber uses very low index contrast between the core and the clad. Here you put a semiconductor core inside a silica matrix, right? Mm-hmm. So do you see in the future maybe going through a slightly doped silicon core inside a silicon clad to try to keep the index contrast low, or is there any advantage that you see? Because I assume it's very lossy because of the big index contrast. So you're working with very short distances. So is that an issue, or how do you plan to go forward with that?
Well, there's two questions there. They are quite lossy, but that's the material at this point. We have worked with a couple of different fibers with low index contrast. So the first ones I showed you, microstructured fibers up there, so they have silicon in the cladding as well. So this essentially enables you to reduce your index contrast. The other ones we've been playing with are some hydrogenated amorphous fibers where you can actually tune the hydrogen content across your fibers, and that enables you to have low index contrast fibers. So there are various options, and for example, if you're going to work with germanium, then you might want to have a silicon cladding as opposed to a silica cladding. But at the moment, what we're really working on is trying to get the losses, get the fabrication right to get the losses down, because these losses are dB per centimetre, and that's far too high for a fiber at the moment.